All right, are we up and running?
Yes, we are.
All right, very good. Well, welcome everyone. Sorry I couldn't be there with you today. It's just the world we live in, I guess, right now for a while longer yet. So I'm excited about talking about some of the different advancements that we're applying in CT and where we're looking at helping accelerate aerospace product development as well as qualification. Those of you that are not familiar with North Star, see if I can get this to move ahead here. There we go. We're a worldwide company that specializes in industrial X-ray equipment as well as digital radiography, or including digital radiography and computer tomography. So we manufacture the equipment here right in Rogers, Minnesota. And then we have worldwide facilities, California, Massachusetts, in England, and in China. And we also provide inspection services at all of these facilities. So I'm going to dive right in and jump through some of the different applications where we've been accelerating the use of CT in the industry. One of them was a really fun project that we did here last year. We took 5 additional industry leaders, and we were all challenged, the 6 groups, to be able to come up with a clean slate, rapid design for heat exchangers. Let me move something here so I can see a little better. Overall, so if you look at the part on the right-hand side, it's a very large, older style heat exchanger design. And then we have the blue section, which is the new design that we came up with. So just summarizing what we ended up doing is we built this with an AM process, and we were able to reduce the number of parts from 40 parts down to 1, doubling the heat transfer within 20% of the total volume of previous heat exchanger. We're able to do that with a 9+% reduction in drop of pressure, as well as 85% reduction in volume, 81% reduction in mass. EOS is the company that printed it. They're worldwide leader in additive manufacturing. This is an aluminum part that they printed for us, and they did it first attempt with no defects when we evaluated it. Then we applied simulation validation of the design and then full validation through testing. So when you look at the different legacy heat exchangers out there, the majority of them were applications were very space constrained. And then there's rising thermal requirements that are continuously changing. And overall, when we looked at the conventional designs out there, there was really little innovation that was taking place with the existing geometries. And so there's a lot of opportunity there anyhow. So the existing systems really involved this pretty much inefficient tube and shell geometry designs, versus with AM, you can kind of start with a clean slate and align all those theoretical stars for flow and pressure and everything else. And with AM, we can generate some geometries that allowed us some pretty substantial improvements in heat transfer, and then some mixing and swirling that you wouldn't get with just a typical tube approach. So here the key technology companies were Entopology. They're the designing group that really came up with the initial designs. And then we can take the ANSYS software and do analysis work as well as build simulation. And then EOS, we sent it to them for the print. And then Stress Engineering Services did testing on it, both at the initial phase here as well as later in full thermal cycling and everything. Excuse me. And then North Star, we did the CT scanning on it, and we could do an as-built there for comparison, send that off to Synopsys. They've got a phenomenal mesh capabilities, and then back to ANSYS again. So when we look at the design aspects here, with Entopology, the capabilities in software allows us to really look at and match the hot and cold fluid volumes, make sure that we're generating a stiff support for whatever the structure requirements are. And then we can isolate, as you can see on the right, the hot and cold regions. And then if you look down below, you look at some of the crazy geometries that obviously you can only do with additive manufacturing. So with CT, we can then capture all of that information and I understand what the true as-built part looked like. So when we plugged these designs into ANSYS, we did 3 different build iterations and then compared them in the simulation software. So looking at it from the computational fluid dynamics standpoint, that helps us evaluate rapidly what is the optimum design performance in the modeling versus building 3 different actual parts and testing 3 different parts. We can create a simulation, and then from the printed part, we generate a CT scan. The CT scan then can be used for generating an as-built model to plug back into the simulation software to make sure that it's actually running it with the actual part dimensions versus the theoretical dimensions from the design. So those of you, if you're not familiar with CT, the real basics, 30,000 foot view is you've got an X-ray tube on the left here, the part, and then an X-ray detector. You rotate 360 degrees around typically, and we capture hundreds or thousands of projections. And from a inspection standpoint, it's critical with these complex geometries to use CT because otherwise you're trying to look through all this superimposed information. Complex geometry makes that even more difficult. And then we reconstructed. Northstar builds all of our own CT systems here. We also write all of our own software, all the way from the acquisition through the reconstruction and the visualization. So if we look at the image processing here from Synopsys, again, they've got this phenomenal meshing program. We import the CT slices, and then from that, we can segment out the structure and actually look at the fluid regions compared to the solid regions. And then on the right-hand side, you can see this independent segmentation that we've got going on. So the key thing here now is we've designed it, and then we've tested it in simulation, but now we have an as-built that we generated from the CT scan. And so now we can compare those two, both in the CFD as well as the CHT programs, simulation programs. And if you look at the as designed here on the left, it was a maximum deformation of 55 microns. And then on the right-hand side, from a pressure perspective, it had max deformation of 50 microns. So very close. And then the last part of the event here was validation testing. So they took coupons and actually did the material testing, looking at yield strength, tensile properties, et cetera. And then we took the actual product and put it through full environmental testing. So shock, vibration, fatigue, pressure and thermal cycling, and flow testing and erosion. And it exceeded all of the requirements. In fact, of course, as guys, we got to blow stuff up too. So they actually ran it to failure, and it ended up running at a pressure of, I think it was close to 10 times or better of what the actual required was. So that also gave us some great feedback to go backwards to say, all right, they could probably thin up the walls and even lighten it up even further. So another really cool project that we got involved with Nair from Wichita State University, Dr. Waruna Senevarati. He's the PhD there that leads the program, and they've got some really cool stuff that they've done with 4D CT. So they have 2 of our X-ray systems there, a really big X7000 where they can put large composite components in, as well as some of the smaller parts. And they even have a load cell built into one of the systems that they can drop in and do tensile and whatnot testing in the machine while they're evaluating with 2D or CT. So 4D CT is basically 3D with time as being the factor of over time, basically. So in this case, what they're doing is they're taking CT scans of parts and they're doing cycle testing on them. So they would do a kind of a stop motion approach of 4D in the sense that what we're going to do is evaluate the interaction between high cycle, low stress, and low cycle, high stress fatigue on these samples themselves. So they developed some coupons, and they wanted to evaluate then from a primary goal standpoint, the fatigue damage in that composites and that growth throughout various fatigue loading. And then secondary to that, they wanted to develop tools for determining, you know, what the residual strength degradation or the wear out of the product. And so the 4D is basically doing a CT scan on coupons and then doing cycle testing on them and then CT scanning them again and again and again throughout different cycles. Another way to do 4D CT is actually doing it while the event is occurring. So if you were doing, let's say, a slow tensile pull or a slow compression load on a part, you just do back-to-back CT scans during the entire process. So in this case here, they're discrete damage modeling of the composites themselves showed these different interfaces here of cracking and propagation of cracking throughout different cycles. And then we compared that to the actual CT scans of the samples throughout those same number of cycles. So in this case here, you look at these periodic inspections, they're looking at cycles, 25,000 cycles, 200,000, all the way up to 1 million cycles. And you can see the degradation of the product, and it's just tearing itself apart here, basically. So the cool thing that they did then is on their own, they took it kind of a step beyond our 4D simulation software. And they built their own program that would allow them to take all of this individual cycle data, all of the individual ply data for each cycle, and then meld those together. So if you look at the top up here, you've got ply 1, all of these different colors represent the different cycles. So the blue is 200,000 cycles, all the way down to the gray, which is 1 million cycles. So what you're looking at in those color variations on the right side is the influence of the crack propagation throughout those different cycles. So you can see how far it extends out in the product based on that. So Waruna has said that he's got an entire paper, in fact, it's over 300 pages long on this material. If anybody wants the full entire data set to be able to look at it, feel free to just email me. So then you'll have access to all of this. I realize I'm flying kind of at 30,000 feet here, but I wanted to give you all a really good overview of some of the cool things that we could do with CT and how it's being applied out there in the industry actually today. Another really valuable tool that we've developed here is what we call our EFX simulation. And you might have heard the term being called out there a digital twin. So in the industry, what we've done is we've taken our standard model systems, the X3000, 5000, et cetera, and we've built a digital twin for that. And what it allows us to do is full offline model specific programming. And we can generate, let's say it's a 2D motion program for 30 different views on a part, or CT scans of multiple parts. We can drop that program that we generate in the model that could be done on somebody's laptop, and then you drop it in the actual system. So when you think about that from the cost of operation, when you have a $500,000 plus X-ray machine sitting there, you don't want to have people spending hours and hours developing techniques when they can develop the technique to the 90+% level and then literally drop the program in and it'll run it and go from there. So here's an example, just the software, what people look at in the software. It's the exact same controls as what we use for actually driving the equipment. So nothing is different from the actual operation of the system other than you have a simulated beam. It's a polychromatic beam, which really gives us a great representation of what it would be if somebody's imaging with the actual system. We can also dump in various alloys of materials. We can dump in fixtures. So basically you just drop a model of your part into the system and load that up, and it's as if you just placed it in your system itself, and then you go ahead and run. So it's actually using the real software, as I mentioned. This also has crash protection built into it. So when you're developing a motion program, for example, you drop it in, it'll match up to the crash protection that you have within the system. So the software interface is literally exactly what we've got in the system itself. And so here I turn on the X-ray system and you'll see the part is placed on the stage. I can actually take that part and position it however I want. So obviously you're typically not going to be inspecting right off the stage. So I would raise it to an elevation that would be representative of one of the fixtures that I would be using. So maybe I've got 4 inches off the stage or something like that. When I rotate the part, it represents what I'm going to actually see on the real machine because it's a polychromatic beam. I can set the kV, the current, the frame rate, everything the same as what I would with the actual machine. So here I'm just centering it a little bit better. I can use that to maybe position the part in different angles to better understand what's the optimum angle to reduce the penetration length on a given part. And then I can take that angle and actually measure it and the distance from there to my stage and establish a fixture formula, basically, to be able to go ahead and create a 3D print formula if I want. All of the variables relative to X-ray principles apply here. So if I change my focal distance, obviously it's going to increase with the inverse square law. In this case, the photon count is going to drop because of the inverse square law and increasing the focal distance. So it's a really beautiful match to the actual system, and this is what the physical structure of the system looks internally. I'm going to jump to some of the high energy scanning. So if we're at our Aliso Viejo facility in California, we have a 6 MeV system from Verax. It's just a phenomenal system. It's the 3.5 and the 6 MeV system there. But the main thing that people forget is it's not just about wall thickness, but actually the full penetration material length that you're dealing with. And so when we talk about high energy, somebody brings us a 1/4 inch thick part, and yeah, you can penetrate a 1/4 inch of Inconel, Hastelloy, whatever, with some pretty low kV. You don't need high kV. However, when you look at something cylindrical, the tangent might be 4 inches, 5 inches, etc. And so some of these big parts could even have thin wall, and yet you still need high energy. So we look at our overall system. This is our high energy system offering. It's typically set up with a 4343 or a couple different detectors, 1611, 1621. We can also drop in an LDA at the same time as a dual detector. You've got the dual spots. The one cool thing about the 9 MeV, which is also an offering, is you've got focal spots that are less than 1 millimeter. So you can generate more geometric mag. This system can handle 3,000 pounds of load, and we've got a virtual detector because of our mosaics, what we call mosaics. It's a stitching capability. We can get a virtual detector of 86 inches in height and 48 inches in diameter. So we can handle some very large parts for both 2D as well as CT. And then we also do helical and what we call subpixel scanning. This was kind of shocking to me the first time I did something like this with the high energy. We're running 6 MeV, but what often we forget is that we have the full X-ray spectra that's coming out of that system. And so as long as you can penetrate it with some of that lower energy, you can get some phenomenal data even at the 6 MeV range. So in this case here, we have a steel structure that has some low density potting material. If you look at the comparison on the left of 450 kV, there's all kinds of scatter. There's all kinds of streaking artifacts due to lack of penetration. A lot of artifacts overall. And on the right-hand side, this is 6 MeV, and we're seeing microporosity inside of the low-density polymers internal and epoxy internal. So just phenomenal capabilities. Another cool project that we did here recently, Cameron Limmer and Matt Keys did a lot of work on this work. We built a simulated rocket nozzle, and EOS did a phenomenal job on printing this for us. We integrated a bunch of different discontinuities, defects in it, so we had a known defect standard or a representative quality indicator that we could use. And so in this case here, we put in multiple defects, anything from 250 micron all the way up to 500 micron. And we positioned them in different orientations of penetration length, as well as different orientations relative to the beam direction. And we can pick up all of these different defects here with the CT scanning. There was only one defect, and I think that was down in the 200 micron range, so 10,000ths of an inch, that because of the laser diameter, we weren't able to detect it, but we're not confident that it's there either. It may have just been fused over. And then once you have this scan, we can pull in the data. In this case here, this is using volume graphics, and we can compare the physical size of the voids or the discontinuities to the actual print design. And we can not only pull the dimension, but we can also pull the actual volume of each one independently. And then what we did here is we intentionally blocked off some of the cooling channels, because one of the biggest issues in AM with some of these type of cooling channel areas is you get trapped powder. So we intentionally block some off. And this is a great example of how you can really isolate and segment the different types of discontinuities that you find. In this case, the trapped powder can be fully segmented, so you got a really good visualization of what's going on within the part. So all of the colors on the right-hand side is actually channels that are blocked, and this is the segmented powder. And then obviously the detection of the defects, as we slice through, we can pick them up in 2D clipping planes, or as displayed on the left-hand side, we can apply them and visualize them in a volume or in a surfaced volume. So on the upper right, you can see one of these channels is plugged with powder. And then on the bottom right, you can see that it's actually capped off on the end. So, and then obviously with, now that you can penetrate the entire part, get X-ray photons through all of these different complex geometry regions, and we can pick up all of the dimensional information, internal and external to the part then. So whether it's looking for wall thickness comparison or just nominal to actual comparison in all of the individual features, as well as just simple 2D dimensions, can all be done with metrology. So that helps really accelerate what it is that we're doing, especially in the additive world, because you can pull all of these dimensions instead of doing cross-sectional work. First article. Another really heavy, large part. So this is an electric motor, 11 inches by 14 inches. And there's areas where we've got 8+ inches of copper and iron. And yet we're able to pick up phenomenal detail here. And the main thing that I was pointing out here on the right is the copper winding wires have a wrapping around it. And you can pick up this wrapping. Very often it's a paper type wrap, or it's a Kapton tape, and that shows up plain as day. Here's an example again of this electric motor, and you look at the internal features that can be very easily cleaned up, very easily seen. And the only thing in this particular scan that has some artifacts is that center region where you have these fins coming all the way across. But this, again, some of these regions end up being 8+ inches of material that you're penetrating. And again, this is with just 6 MEV. And some gearbox is very large. So this is crazy size. Some of these gears are 8+ inches across, and stainless steel. And yet we're getting, the ball bearings around them showing up very well. And the dimensions across, we can do all kinds of dimensional work on this. So another application for CT that's been real helpful in especially building brand new connectors, designs, and things like that is, instead of doing DR imaging like on the left, which can take typically 2 to 4 views, 5 to 15, 20 seconds. We can do a very quick CT scan. We've done these in as little as 15 seconds all the way up to 3 minutes. And the cool part about it is on the left, you're doing all of this information inspection through superimposed features, versus on the right, I can isolate a single row of pins, and then I can isolate the other row of pins and zoom in and out and look at the whether there's bird caging going on or whether there's shorts, etc. And we can do that, like I say, in just a very quick amount of time. The scan time is a little longer than the imaging acquisition time for DR, but the interpretation can be much less and more accurate, a higher probability of detection. The same type of thing goes on here with silver braze inspection. So this is an aerospace fitting. And if you look at the braze joints, you've got superimposed information on the 2 DR images, great images, and I can see all the voids, no problem, but what's front, what's back, how do I know? And with CT, what we can do is a very quick 40-second CT scan, and then we can do an unroll feature and look at those individual voids as if I cut the part open and laid it out flat. So from a 2D inspection standpoint, really valuable, and most of the criteria that's already established is 2D criteria. But if you can apply 3-dimensional criteria to it, you can actually do something like this where we segment out the braze and we completely isolate the braze. Just look at the braze. We can do percentages. We can do void analysis. And this can be set up in volume graphics, for example, as a assisted defect recognition routine. And it's just really cool. Great visualization. It's as if you're looking at a transparent part. And then the same type of thing applies here with aerospace. This is titanium welds that are very critical, very thin wall thickness. You can see some porosities on the left. And the only way that we know that it's tube side only or detector side is by rotating the part around. But if all you have is 3 images that are static, it's very difficult to determine that. Again, in CT, we can slice this in any plane. And so on the right-hand side, we can slice down from the top, and we can do what's called a fixed slice. And so we could take that entire weld and summarize it in that slice and build it up so we can see all the defect as one. Or we can also just simply isolate it here on the bottom and slice it open and roll it out, lay it out flat, and then interpret it that way. So much quicker interpretation, much higher probability of detection. And then the same type of principle applies here in volume graphics, or in our software, we can do a visualization like this, where we can isolate it as if we're looking at a transparent part. And then obviously in software like volume graphics, we can do full analysis of that, porosity analysis, look at volumes, look at diameters, and look at the spacing between them. And some of you are familiar with our Subpixel process. So basically what it amounts to is we take the detector and we shift it in different orientations so that we basically take 4 images of a region of interest with 1 pixel. We're moving a subpixel amount of information. So we've had this available for many, many years. However, something cool that we've done recently is we've developed a means for us to very consistently produce what we call continuous subpix imaging. So the continuous subpix allows us to do very fast CT scans and do it very accurately and be very high resolution capability. So on the left-hand side, we've got a subpix that was 20 minutes. The goal was a 20-minute routine here. And on the left, we've got an 18 minutes standard scan. And the primary difference that you see is there's less information. It's more of a blur on the right-hand side. One has a 10 micron voxel, the other has a 20 micron voxel, even though it's the same geometric magnification and everything else. So now with this new innovation, we can do subpix scanning 4 times faster than previously, because previously it would take 4 images. So basically it's 4 times longer generally than a standard scan. And now we can do that 4 times faster. So we can actually do this extremely quick. On the left-hand side, you've got a 1-hour CT standard scan, and on the right, we've got a 58-minute continuous subpix scan, 39 micron versus 79 micron. So very crisp overall. And then on the left here, again, a 1-hour scan, and then we have a 10-minute continuous CT scan, subpix, and again, much, much crisper image on the right-hand side. I just want to thank everybody in the team that helped put all of this together. The big group here in topology and ANSYS, Synopsys, EOS, and Stress Engineering. Those are the folks that work with us specifically on that heat exchanger. That heat exchanger was literally only about 6 inches by 4 inches in diameter. So they're able to really maximize that performance with a very small package. And then Dr. Waruna, thanks to him for helping us put together that information on the dynamic and static fatigue testing with 4D. And then this is our team on the right-hand side here from Northstar. They'll put all this material together. So with that, thanks a bunch for taking the time. And if you got any questions, feel free to ask. If you get an opportunity, please stop by and see Jan over at our booth 14. And anybody have any information, any questions, or want that presentation from Dr. Waruna or any additional details, just contact me at this email address. That'd be great.
Thank you, Brett.
Yep.